Welcome to Online Precalculus. This is section 3.2, Logarithmic Functions. Our objectives for this section are to change from logarithmic function to exponential form and from exponential form back to logarithmic form. Then to evaluate logarithms, use basic logarithmic properties, graph some logarithmic functions, talk a little bit about domain, and then talk about the two most common types of logarithms, the base 10 common logarithms and the natural logarithms. So first, when we start our discussion of logarithms, we are going to start by talking about how it is the inverse of an exponential function. Inverses were from a previous section, section 1.8, and what should you already know about functions and their inverses? Well, first, only one-to-one functions have inverses that are actually functions. A function f has an inverse function, f inverse, if there is no horizontal line that intersects the graph at any more than one point. Okay, so that means that in order for a function to be one-to-one, every input must be different. That's what makes it a function. And every output must be different. That's what makes it a one-to-one function. If a function is one-to-one, its inverse function can be found with the switch and solve strategy. Switch x and y, solve for y. And then here's some basic rules for inverses. If f of a is equal to b and f of inverse of b is equal to a, right, domain and range is switched, right? You find inverses by switching x and y. The domain and range of a function and this inverse function are also reversed. The inverse property applies here where we have f of f inverse of x is equal to x, right? They undo each other either way you put them into each other. And the graph, which we're going to do some graphing, the graph is the reflection of the graph of f about the line y is equal to x. So let's start with the definition of a logarithm. Okay? So if you think about an exponential function, right, our exponential functions look something like that. There is no horizontal line that hits the graph at more than one point, right? It looks like it's horizontal on the bottom here, but it's not. It's just going down very, very slowly. So that means that this exponential function is one-to-one, and it has an inverse. But if you start with the switch and solve strategy, right, you switch x and y, how do you get y by itself, right? So you could try to take maybe a square root, but that wouldn't get y to itself. You can try a y root, but now you have x to the 1 over y power is equal to b. Like nothing that we have previously studied is good for this. Okay, we don't have a method for getting y for solving b to the y is equal to x. In order to do this, we need a new notation, and that is called logarithmic notation. So this notation gives us a way to name our inverse of the exponential function, and it is called the logarithmic function with a base of b. Okay? So if I look at the definition of a logarithmic function, there are some restrictions. X has to be positive, b has to be positive, and it cannot equal 1. Okay, and this all comes from the way that an exponential function is set up. Okay, because we don't have bases that are 0 for an exponential function because nothing would happen. We don't have bases that are negative because that would give us imaginary numbers with fractional exponents. And we don't have a base that is 1 because, again, nothing would happen. Okay, so the same restrictions are part of a logarithm. So if my logarithm looks like this, y is equal to the log base b of x, it is equivalent to b to the y power equals x. Okay, this sort of reversed or exponential function turned around. This is the logarithmic function with base b. And notice when we compare here, logarithms are functions that give you answers that are exponents in my exponential function. And that's what we're going to talk about right here. So my equations are different ways of expressing the same thing. Both of those are equivalent to each other. First one is logarithmic form. The second one is exponential form. And like I just said, notice that in the logarithm, y is an exponent. Okay? And if you compare the two different forms, the logarithmic form and the exponential form, you'll see that the bases are the same. They're in different places, but they're still the same number. The exponent in one, the exponent in the exponential form is different from where it is in the logarithmic form. And notice where the x is in each one. And we can use this relationship to go back and forth between the two of them since they are equivalent. Okay? So let's do that. Let's change each of these equations into its equivalent exponential form. So to back up for a second, if we have my exponential form, just notice where all the pieces are. Okay? So exponential form, the base is 5. Answers to logarithms are exponents, and it is equal to the part inside the logarithm. The base is b. The answer to a logarithm is the exponent, and that's equal to 64. Now we could solve for x, right? We say, oh, it's 25. We can solve for b, we can say it's 4, right? But that's not what the question is really asking. It just wants us to rearrange these. And in the last one, 3 is the base, y is the exponent, and it is equal to 7. A few more. 7 is the base, 3 is the exponent, and it is equal to x. Answers to logarithms are exponents. I'm going to say that a lot because that's the most important part to remember, is that when you're solving a logarithm, the answer that it spits out is the exponent that turns the base 7 into this number. And in this case, that would be 7 to the third power, which is 343. Okay, so here we have the base b squared is 25. The base 4 to the y power is 26. Now that one's a little bit harder to figure out, right? Because I can sort of visualize the 5 here. I can easily calculate x there by just raising 7 to the third power. Trying to guess an exponent that is not a natural exponent of 4 is going to be much more difficult. Okay, so here for part C is something that we might need a calculator for. So much of what you've discussed so far involves changing from logarithmic form to the more familiar exponential form. Is there a pattern? Yes, and there is, and you can sort of see it sort of goes around, right? We go this way to the y, then we hit the equal sign, then the x. So b to the y power equals x. Okay, that sort of helps a little bit. Go from the bottom to the exponent, then back over the top through the equals. But whatever method you I like to just remember that the bases are always the same. The bases are b, and the answer to a logarithm is the exponent, and that is the part inside because that's what's left over. Let's go the other way. Let's change from exponential to the equivalent logarithmic form. Okay, so now you are actually going to have to write the word log. Right? We put the base as 12 because that is the base of the exponential function. It's always the same. X is equal to 2. Answers to logarithms are exponents. So here we have log base b of 8 is equal to 3. And here, for this one, we'll talk more about this later, but we can have the log base e of 9 is equal to y. Okay, there's a shortcut for that. We'll get to that at the end. Okay. So again, write each in logarithmic form. So that's the log of 2. Log base 2 of x is equal to the exponent 5. Log base b of 27 is equal to the exponent 3. The log base e of 33 is equal to the exponent y. So remembering that the logarithms are exponents makes it possible to evaluate some logarithms by inspection. Okay? And as you start to get a little more used to logarithms, this becomes a little bit easier. So the logarithm of x with base b, log base b of x, is the answer is the exponent. It's the exponent that takes you from b and gives you x. So for example, log base 2 of 32 is what power does it take you to go from 2 to 32? And it is 5, because 2 to the 5th is 32. Okay, so we can do that with these problems. Log base 2 of 16. What power do you need to raise 2 to 16? And that would be 4, right? 2 to the first is 2. 2 squared is 8. Oh, no, 2 to the third. No, 1, 4, 8. Yeah, sorry, I forgot 4. 4 is 2 squared. 8 is 2 to the third. 16 is 2 to the fourth. Next, with a fraction, the log base 7 of 1 over 49. Remember that 49 is 7 squared, but in order to get a fraction, you need a negative exponent. So the log base 7 of 1 over 49 is negative 2. Log base 25 of 5. What power do you raise 25 to get 5? Now we're getting smaller, not fractions, but we're making the base get into a smaller number. We use roots, fractional exponents. Fractional exponents are roots. And another way to think about part D, if I rewrite this as a fractional exponent, right? The fifth root of 2 is saying 2 to the 1/5 power. So now this is basically saying, what power do you raise 2 and you get 2 to the 1/5 power? Well, that's just 1/5. Okay, and that's going to be one of our properties that we'll look at later. A couple more. That is 2. 10 squared is 100. 5 to the negative 3 is 1 over 125. 1/2 for 6 to 36, square root, and 1 over 7 to change 3 into the 7th root of 3. And all these can be done in your head, or if you need to, you can put it into a calculator if your calculator lets you do things like this. So let's look at some basic properties that could help us. Okay? Because logarithms are exponents, they have properties that can be verified using the properties of exponents. So the log base b of b is equal to 1 because in order to turn b into the same thing, you're asking yourself, what exponent do I raise something to and have it not change? And so that is 1. Okay? Log base b of 1 is going to be 0 because anything to the 0 power is equal to 1. So to change b into 1, we get 0. Okay? So again, using these properties, the log base 7 of 7 is going to be equal to 1. And the log base 5 of 1 is going to be equal to 0. Not a lot here. Still 1, still 0. Okay? So again, we're thinking how to get to the base, how to get the base to the inside of the logarithm. Now that we have talked about logarithms a little bit, we can finish our switch and solve strategy and actually find the inverse of my exponential function. So we start with my exponential function, switch x and y, and now we rearrange it into the logarithmic form. Y equals log base b of x, which is a function, so I can write the inverse. So that means that the inverse function of my exponential function is log base b of x. Same base. Notice that my log and its inverse are going to have the same base. Inverses undo each other. These two properties hold for all inverse relationships. So that leads us to two inverse properties. I could put the exponential function inside of a logarithm and the logarithm inside of the exponential function. And in both cases, I get them to undo each other and get just x. Again, so problems like this, the first one's a little bit easier to see, but log base 4 of 4 to the 5th power, we can use my inverse property just like I did with the fractional exponents before, and this is going to be equal to 5, and then this one is going to be equal to 9, because these are the two bases that match up. Those are the two parts of the function that undo each other, 6 to some power, and the power is the log base 6 of 9. The 6 and the log base 6 undo each other, and we're left with just 9. Okay, same thing with these two. This one's going to be 8, and this one's going to be 17. As long as these two match, as long as the bases match, these two functions undo each other. If they didn't match, now you got a problem. So, how do we graph logarithmic functions? There's a couple ways. We can use the fact that logarithm functions are inverses of exponential functions. So that means that the logarithmic functions reverse the coordinates of exponential functions. It also means that the graph of the log function is a reflection across the line y is equal to x. So you can keep all that in mind and graph the original function and then graph the logarithm. We'll do it with two different colors there. Graph the logarithm and sort of compare the two. What I like to do, and we'll do this in the next problem, is I like to go right to the logarithm and graph the logarithm without doing both of them. But let's compare the two of them anyway. Okay, so if I wanted to, I can make a table for my exponential function, right? If I plug in some negative numbers and some positive numbers, 2 to the negative third power is 1/8. That would be 1/4, 1/2. Anything to the 0 power is 1. 2 to the first power is 2, 4, and 8. So as I graph this, 2, 4, 8. Let's plug in a 4 there just for fun, 16, since I have one that goes this high. Okay, and then as I graph this function, you can see it looks like a typical exponential function. Okay, let's graph the logarithm. And again, if I were to make a table for the logarithm, I could just reverse the numbers, switch x and y. Right? This is 1/2 gives me -1. This is 1 gives me 0, 2 gives me 1, 8 gives me 3, and 16 gives me 4. Right? And again, what are you doing? So you put a 16 in here. You're saying what power, what exponent makes a 2 into a 16? Oh, it's the 4th power. Okay? And so you can see, as I go to 1/8, I get -3. As I go to 1/4, I get -2, half. And this is the coordinate right there. 2 gives me 1. 4 gives me 2. 8 gives me 3. 16 gives me 4. And you can see that these two graphs are reflections of each other. Across the line, you can see the line y is equal to x. Right there. All right. And each one of these coordinates has its opposite. So this is the coordinate of 3, 8. And so we have 8, 3 on the inverse. Okay. The trick to graphing a logarithm is to find these numbers, to plug numbers in that give you points that are easy to graph. The other part to recognize is that the x or the x asymptote, or sorry, the x axis is a horizontal asymptote for the exponential function, and the y-axis then becomes, right, switch x and y, the y-axis then becomes a vertical asymptote for the logarithm. So knowing that the logarithm is going to have a vertical asymptote, and it makes sense because this, try it on your calculators, is undefined. There's no power, right? What do you put in this box right there to give you a -1 or in any negative numbers? Okay, you cannot raise, and look at the exponential function, right? It never gets negative. No matter how far left you go, it never gets negative. Okay, so it implies that there are certain functions of, there's certain parts of an exponential function, because they're inverses with logarithms, there's certain numbers you can't get in exponential functions, which means there's certain parts of the x-axis that are undefined for logarithms, since x's and y's switch. Okay, let's try to graph another, except this time let's not graph 3 to the x. Okay, let's just go and graph y is equal to the log base 3 of x. What numbers do I plug in here? Well, I could start with fractions. I don't want to. Let me start with 1. So plug in 1 there. I get 0. Okay. I don't really want to plug in 2. 2 doesn't work with the base 3. Okay. I don't know what power you to raise 3 to give me 2. It's going to be something bigger than 0, but it's not going to be 1. I'd much rather say 3, 1. Again, why plug in 4, 5, 6? You need a calculator for that. How about 9, which is 2, 27, which is 3. And now by graphing those, 3, 1, 9, 2, and almost to 3 back over here. And then by realizing that as I put in fractions, right? So 1/3 is going to be -1, 1/9 is going to be -2, right? This graph, 1/3, 1/9 is going to get closer and closer to the y-axis, but never actually touch. It is a vertical asymptote, and we can relay that with a dotted line if we want to. Okay, so when I graph logarithms, I usually try to graph the vertical asymptote first, and then graph key points that work well with the base. Okay, and so here are the two types of exponential functions: growth and decay, with base bigger than 1 or between 0 and 1, and the corresponding logarithms. In both, you can see that if it's exponential in the first graph, if it's exponential growth with the blue line, we now have logarithmic growth. It's still growing from left to right, but it just has a different shape. And the same thing with exponential decay and logarithmic decay. Both functions going down, but now they just go down at different rates and look slightly different. Okay? So, characteristics. So that figure tells us a couple of characteristics of logarithms. First, the domain of a logarithm consists of all positive real numbers from 0 to infinity, but the range is all real numbers. Okay, so this is switched from an exponential function, which makes sense because they're inverses. Okay, so now my logarithm is only defined from 0 to infinity. Graphs of logarithmic function pass through the point 1, 0, which is opposite of an exponential function, which is 0, 1. The x-intercept is 1. There is no y-intercept. If the base is bigger than 1, it goes up and to the right, and it is an increasing function. If the base is between 0 and 1, it is decreasing. And the graph approaches but does not touch the y-axis, and it has a vertical asymptote. You can still move them around. Okay, we can still transform my logarithmic functions just like I would any other function. So if I want to move it up, I add something, or down, subtract something to the outside of the logarithm. Right or left, I would add or subtract something to the inside of the logarithm. Reflection in the x-axis goes in the front. Reflection in the y-axis puts the negative inside the logarithm. A number in the front vertically stretches the function if it's bigger than 1. It vertically shrinks the function if it is between 0 and 1. And a number inside the logarithm horizontally shrinks the function if it is greater than 1, and horizontally stretches the function if it is between 0 and 1. So here are a couple more examples of how these transformations work. Again, I would always start graphing a logarithm by first drawing the vertical asymptote and then using points that work well with the inside of the logarithm, that work well with the base of the logarithm in order to graph the rest of the function. So if I had a function like this, I would plug in, well, the vertical asymptote hasn't changed because that's shifted up 3. I would plug in 1. What do you get? Plug in 1. You would get 0 for this part plus 3, and you can see that on my function, I would get 1, 3. Okay, and then, of course, the other properties hold. The negative in the front, you can see the reflection across the x-axis in the second figure, and the third figure, you can see the reflection across the y-axis. With a negative inside there, right? Now, if I put a positive number in, that's trying to take a negative logarithm. So that is undefined. So you'd have to put a negative inside that, and that's why it is reflected. Okay. So let's talk a little bit about how to figure out where a logarithm is defined. So in 3.1, we learned that the domain of an exponential function is all real numbers, and the range is positive numbers. And because the logarithm is the inverse, it reverses the domain and range. So the domain of a logarithmic function in the form log base b of x is the set of all positive real numbers. So that means this is defined because 8 is a positive number. However, negative log base 2 of negative 8 is not defined. Log base 2 of 0 is not defined. Okay, that means that I have to look inside the logarithm. And in general, the domain of the logarithm is everything that makes the inside of it greater than 0. Not greater than or equal to 0, because 0, you cannot take the log of 0, just greater than 0. So that means that if I want to find the domain of this logarithmic function, I don't need to know what base it is. All I need to say is that the inside of this logarithm must be greater than 0. So that means x must be greater than negative 3, which makes the domain of my logarithm not a bracket, because I don't want to equal to 0, negative 3 to infinity. Find the domain of this logarithm, log base 4 of x minus 5. Again, it doesn't matter what the base is. All I need to know is what makes the inside of the logarithm greater than 0. So x is greater than negative 5, which makes my domain from negative 5 to infinity. Okay. Next, let's talk a little bit about common logarithms. So we write a square root of something. You don't put a 2 there, right? We just leave it blank. If it's something different, we put that number, 3, 4, 5, whatever. But a square root, we just put the symbol for square root because it's the most common, because it is the root that is taken the most often. Same thing we can do with common logarithms. So a function with a base 10, a logarithmic function with a base 10, is typically called the common logarithmic function. So this is because our mathematical system, works with base 10 numbers. Every time you add a digit, right, you're adding a power of 10. It happens to be the logarithm that happens the most often. Again, that's why it's called common. So instead of writing this whole thing like this, if this base 10 is the logarithm that happens the most often, we can just leave it out, just like we would with a square root. And so if you see a calculator with just the word log, that is really a base 10 logarithm. Okay. If you happen to get an error message, right, if you try to type this in and get negative 3, you might get non-real answer, you might get undefined, you might get error, something like that. Remember that the domain of common logarithms is the same as the domain of a regular logarithm. It must be greater than 0. Okay. Many real-life phenomena start with rapid growth, and then the growth begins to level off, And this is why we can use logarithmic functions to help us model some of these. So let's model the height of a child. So the percentage of adult height obtained by a boy who's X years old can be modeled by this logarithmic function, where X represents the boy's age from 5 to 15, f of X represents the percentage of his adult height. How much of his adult height will he get by age 8? So basically, we're doing f of 8. So this is 29 plus 48.8 times the log. You don't see a base. That is a base of 1, or sorry, a base of 10. And we just plug in 8 to our function. Logarithms act like the inside of parentheses, so you're going to have to do that first. So the first thing I want to do is do the log of 9. So that's 29 plus 48.8. The log of 9 inside the parentheses first, and then the logarithm is 0.9542. Typically, we leave 4 decimal points for logarithms because they are exponents. Small changes make a big difference. Okay? So adding these all together, we get 75 point, we can just say 75.6%, right? This function outputs a percentage. So that means that at age 8, this boy reached 75% of his adult height. 10, so we're going to get f of 10. And so the function was 29 plus 48.8 log of 10 plus 1. So we get 29 plus 48.8. I evaluate the log of 11. I get 1.0414 times the 48.8 plus 29 gives me 79.8%. Okay. Good to know. And we use these logarithms, right? Because the function, this works for this type of function because you grow very fast and then you sort of taper off. Eventually, this function wouldn't work anymore, which is why it said it was only defined for age 5 to 15. But yeah. So the basic properties of logarithms that were listed earlier in the section can also be applied to common logarithms. So here on the left are the general properties. Here's what they look like with common logarithms. You see, it's just the same thing, except instead of putting a base b, I just leave it blank because it's base 10. Okay? And now I can be specific with these numbers, right? Because we're using a specific base. So the log of 1 is 0. The log of 10 is 1. The log of 10 to the x power is x, and 10 to the log x power is x as well. And this property can be used to evaluate common logarithms with 10. So the log of 100 is 2, 1,000 is 3, right? And so on. Log of 10 to the 7.1 power is 7.1. So we can use this idea to measure magnitude of earthquakes. The Richter scale is a logarithmic scale. So is the decibel scale. So things you might have heard of before that actually use logarithms. So here's the formula for the intensity of a earthquake, where I sub O is the intensity of a barely felt 0 level earthquake. The earthquake that just destroyed San Francisco in 1906 was 10 to the 8.3 power times as intensive as a 0 level earthquake. So what was its magnitude on the Richter scale? Well, if I look at my formula, this is kind of a silly, it's more interesting to calculate these Richter scale numbers without a comparison. But basically, all this is saying is that your I is 10 to the 8.3 power times bigger than the initial one, over the initial one, so those just cancel out. And so really what we're doing is we're finding this expression, which is just 8.3. Log base 10 of 10 to the 8.3 power is 8.3. So look how much bigger this was. 10 to the 8.3. So that's a 10 with 8 zeros and a little bit extra, but 8 zeros on it. So that is many, many times bigger. Okay, so the Richter scale, small moves up and down. Each number in the front of a Richter scale is a power of 10. Okay, so earthquakes with big numbers in the Richter scale get very, very intense. All right, let's finish our talk about logarithms by talking about natural logarithms. So just like the common logarithm, which looks like that, okay, natural logarithmic functions with a base e are the second most popular logarithm because they're used in all sorts of applications for real world situations, right? Just like the common base exponential function. They're good at modeling real world applications. So instead of writing the log base e of x like this, we wanted a shortcut. So the shortcut, plain old log was taken because it was a natural base, because e is the natural base, we use the letters for natural log, ln. ln of x. That is an ln. It is not an I. It is an ln. It stands for natural log. Well, why not nl? And that is a little presumptuous to assume that the ancient Greeks spoke English, because they did not. So the people who came up with logarithms spoke Latin. In Latin, natural log would be read as Logarithmus Naturalis, LN, not NL. Okay? A lot of mistakes students tend to make is, again, thinking that is a capital I, and it is not LN. LN. So you can see that on most calculators. If your calculator has a log button, it probably has an LN button, probably right next to it or above it or near it somewhere. And it's probably near the button that lets you take e to some power. Okay? Natural logs are just logarithms, right? They are still logarithms. They just have a different base. So all the properties apply. Again, that means the domain has to be greater than the inside of the natural logarithm has to be greater than 0, and all my other properties that we previously talked about still hold. So again, you want to know the domain of this natural logarithm. It is everywhere that the inside of the logarithm is greater than 0. Just be careful with this, because as you multiply both sides of an inequality by a negative number, you must reverse the sense of the inequality. Therefore, the domain of this function is from negative infinity to 3. And this one is interesting because x minus 3 squared greater than 0. When I do that, you know, when I don't even have to do anything, right? Because when I think about this, is if you squared something, how are you going to make something that's squared into a negative number? And you really can't. And if you think about this parabola, and if I want to solve this, right, you would find the two roots. The two roots would be negative radical 3 and positive radical 3. And this is a parabola where both ends open up. So this is positive. Never mind, sorry. The roots of this equation, it is a double root. It is a radical 3, okay? And both ends of this function go up. So the only place that this function is not greater than 0 is at 3. What am I doing here? 3. Why am I putting radical 3? I don't know. I'm crazy, right? Square root, add 3 to both sides. Blah. Okay, so the domain here is from negative infinity to 3 union 3 to infinity. Okay, that's okay. So again, we'll get this one right this time. Subtract the 4 from both sides, negative 4. So x is less than or equal to a positive 4. So my domain is from negative infinity to 4. And here my root is 0, right? X squared has to be greater than 0. Square root x is still greater than 0. And where is that true? That is true on both sides of that on this parabola. And so the domain is from negative infinity to 0, union 0 to infinity. Okay, so taking the square root, not the best way to find the solution of an inequality with a polynomial. Better to graph it and make our little sign chart like we just did there. Okay, but the basic properties of logarithms that were listed earlier can still be applied to natural logarithms. Instead of a base b, this is now just a base e. It is just the same thing. It is a natural logarithm. It is just the log base e of 1 is still 0. The log base e of e is still 1. Okay, so even though you don't see the word log and you just see ln, it still means a logarithm with a base of e. So last example here, temperature in an enclosed vehicle. So when the outside air temperature is anywhere from 72 to 96, the temperature in an enclosed vehicle climbs by 43 in the first hour. So you can see from the bar graph, but more importantly, we have our equation. So if you want to know how hot this gets after 50 minutes, we can find f of 50, 13.4, natural log of 50 minus 11.6. Just be careful. This is not in parentheses. So you do the natural log first, then the multiplication, then the subtraction. So, so this turns into 13.4 times the natural log of 50 is 3.9120 times 13.4 minus 11.6 gives me 40.82. Pretty close. My graph overestimates slightly, right? It's just not as accurate, but now we have the exact answer in case we want it. So to finish off here, there's a lot about E that we don't cover in pre-calculus, and it's mostly discussed in calculus. One thing you should know is that E is named by and after the mathematician Leonhard Euler. Euler's constant, right? E, right? See the E? So comes from his name. And he proved, like we said in the previous section, he proved that it is the limit of 1 over 1 to the n power, 1 over 1 plus 1 over n to the nth power as n approaches infinity. He also proved this relationship that e to the I pi is equal to negative 1. It has a cool pattern to it, much cooler than pi, right? 2.7, 1828, 1828, 4590, 45, and then it just keeps going after that in a less defined pattern, but still pretty nifty. Easy way to remember it is 878 over 323. Newton showed these relationships with the infinite sums, and of course area under the curve, which is something that is used in calculus all the time. It can be shown with natural logs, and it's actually the first time a mathematician used logarithmic functions for something other than just computing numbers to actually find some area underneath the curve. Okay, so that was section 3.2, logarithmic functions.